Alright guys, welcome back. This is really exciting. This is actually the first time I have had all of the parts out. It's pretty much 99% of the parts here, except for the steel for all the frame, the actual body of the machine. These are all the mechanical parts and they're all in one place, which in the last video I said I've been collecting it for probably like more than 2 years. And yeah, so it's pretty exciting to have it all in one spot. My name's Hayden. I run a natural building company called Curvatexture, and the purposes of this video is to begin building a DIY render pump that'll spray render and plaster, both lime, cement and natural clay renders, spray it from a hopper, spray it onto the wall so that we can plaster much faster. So I have been carrying around these parts for ages, and here's the original drawings that I originally drew to figure out the beginnings of all this. They've evolved a bit onto the computer-aided designs that I showed you in the last video, but yeah, this is where it all started. The whole thing, I'll just run you through section by section and kind of part by part. The whole thing started with this gearbox here. It started with an idea that I wanted to build one, and then a good friend of mine, Daz, thank you very much, Daz, the tool guru from Castlemaine, he gave me this, which is a gearbox made in Italy, and it's a 1:49 ratio gearbox. So that comes into play. In the last video I said that I sat in front of the JMC video and counted the revolutions per minute to be able to figure out how fast I needed to make the render pump spin, and I came to somewhere between 40 to 48 RPM, somewhere around there I think. And so that comes into play for sure when we need to figure all this out. So I got given this, thank you very much Daz, that's really kind. This I bought. I also have a spendings list that I've been just keeping a tally along as we go. So I got this for free. I bought this for 90 bucks off eBay. It's a 2.5 horsepower, 240 volt, 240 volt motor, and it actually has a forward and reverse switch, which is really cool. And that is really cool, but I'm quite certain I'm going to put a speed regulator on it so that I can slow down and speed up the whole machine as well, so that I can dial it in and get it really perfect. Because at the moment this is all complete guesswork. I don't know if this is actually going to be, if this gearing ratio is going to be the best functional ratio for it. So yeah, 2.5 horsepower, nice beefy one. The one in the JMC video that I'm basing like this whole build off was much smaller than this. So, and that was really pumping a lot of render at quite a speed through quite a long hose. So I'm really hopeful that this one's gonna be fine for it. The biggest question mark for strength of this whole unit, I'm kind of over engineering things a bit. I'm pretty happy to do that, to have a bit more strength and just a little bit more security. The thing that I'm most worried about is this tiny little shaft. So this is a 14 mil shaft. I got quite a bit of, I got a lot of shafts and a few things milled up at the local steel fabrication place, and this was one of them. So it's a really high, it's not just mild steel, it's higher grade than that. But the whole crux of the entire operation runs on the strength of this pretty much, or more so this is the smallest, weakest link, I would say. So yeah, we're just gonna have to see how that goes. So this is a 14 mil shaft. Coming off here is a 25 mil shaft. I originally spoke to another turner friend, like a steel fabricator in Melbourne, who was a family friend, and I was chatting to him to get quite a few parts done, and one of the parts was going to be this coupler, but we we started doing the maths on it, and I wanted to get quite a few other parts done as well, and it was just going to be too expensive. So, but two reasons. One, it was going to be too expensive, and if we were to get this coupled, this coupler turned out of solid steel, going from 14 mil on this side to a 25 mil on this side. If it's solid steel, it has no flex in it, so so the way that I build is very backyard, and it's very, very imprecise. I try and be as good as I can, but I can only be as good as I can be. So the amount of inconsistencies that there will be in this build will be quite high. So if the mounting, say the mounting bracket for this versus the mounting bracket for this are ever so slightly off, even a fraction of a millimeter, and this coupling is dead solid, it will wear either the bearings out in here or the bearings out in here, or the bearings out of both, or cause more damage than even just the bearings. So these are a cool thing that I didn't really know existed. They're a coupler, and this is some sort of plastic, and it can take, I think this one's rated to 3 ton, which is pretty good, but it has the ability to ever so slightly wiggle and move and shift, so it can turn, and it doesn't matter if you're a few mil out, because the inconsistency is going to be made up by this, which is really, really cool. So that's that. That sits there and goes into this one. So the RPM of this is 1400. I'm looking back over my notes here that I wrote probably 2 years ago or more. This goes, this is 1400 RPM, and this gearbox reduction is 1 to 49. So once it comes out of here, it changes direction. It's a worm drive, a worm drive gearbox, so it actually changes direction 90 degrees as well and comes out here. And when it comes out here, it comes out at I've only got the final calculation, 1400, yeah, sorry, it comes from 1400, and this pulley is then turning at 28 RPM. So that ratio through here of 1 to 49 pulls this down to 28 RPM. So we've got 28 RPM coming off here. I could have done a single V pulley, but I did a double. We've got the double belts here, and I gave myself enough length to play with. I did just a really quick layout before I bought these, just to make sure I had enough length to play with, because I didn't know the exact positioning of this mechanism in reference to this. So I gave myself a bit more there, yeah, which I'm really happy with. And this is a larger sprocket. This is the 6-inch going down to the 4-inch. So this one will spin faster than this one. So it pulls us up, because if we kept it at the 28, the video RPM that I counted on the video was around 40 or 45. So this pulling up to this pulls us up to 42 supposedly, if all my calculations from 2.5 years ago are correct. And if that's correct, then this pulley here will be rotating at 42 RPM, which I'm really happy with. But like I just said, I'm going to be replacing this with a speed regulator, big proper chunky, yeah, proper 240 volt speed regulator for motors of this size, and I'll be able to digitally control the RPM, so and the direction of it too, which is cool. So I'm not too worried about that, but I wanted the system, even if it wasn't working with the, even if we didn't have the speed regulator up and running, I wanted this to be working as accurately as possible. So this then goes to this, and then we have one pulley here for housing. I'll move the camera and get a better shot. So here you can see my wonderful schematic from 2 years ago, but I won't reference that too much. Pretty much just run you through quickly what's going on here. So here's the double V pulley, which has come off the larger 6-inch. this whole shaft, I got a keyway cut in the whole thing because I didn't know exactly where all of these parts needed to fit yet. I'm not always the most organized with drawings, as you can see from my schematic, so it probably would have been relatively useful to map all this out in SketchUp and get it all cut up very precisely, but that's just not how I work sometimes. So I got the basic length that I knew I needed the shaft, and yeah, got it cut. So this one can accept a key steel to be able to key it in and lock it in so that it can rotate. So that'll transfer really well onto the shaft. We have an outer bearing here which will just go into the steel tube housing of the machine, and then the spacing of all this will move a bit, and it's going to be quite tight as well, but that's not the worst thing. And then yeah, so we come onto here, and this is a faceplate bolting bearing, which will bolt onto a faceplate which will sit in here. So the faceplate is going to be a really, really large piece of plate steel, which will be the frame ultimately, or the housing for the whole rotor system. This is a weldable hub with a key steel in it as well, so I can put key steel on that and key steel on that, and then this piece will have a large hole drilled in it. So we'll have a big hole drilled in it, going through both sides so that the shaft can slip through, and then I'm going to weld off the shaft. I'm going to weld these two hubs onto it so that these hubs will key into the shaft and then transfer the force into this rotor shaft. There'll then be the second piece of steel here, which will then take this final faceplate bearing here, and that'll all bolt in. So then the whole thing can bolt together, and yeah, next I'll run you through how this rotor is actually going to work. So this rotor is the pretty much key to the whole operation. It's the part that's going to be moving the most, like physically it'll be making the most distance, and it'll be taking a lot of the load. So although I could have, for the rollers of it, the actual wheels that are going to squeeze the tube, which I'll get to, I could have bought them from Bunnings or Hardware or whatever, but I just, every time I went in there, I looked at them and I just looked at the bearings and I just thought, they're just the cheapest possible bearings, you know, like caster wheels and things like that aren't made to roll any real distance, any real speed, or be under any real force. So I just really felt that it would be really good to get them properly machined up by my friend. So that is the job that he ended up getting done, and I ended up buying the rest of the parts like I mentioned. So these are some of the most expensive parts yet. Both of these cost $350 to get made, but yeah, the bearings in them are loaded to 3 ton. Those bearings, they're precision centered, so they're going to be rolling absolutely dead center, and they also have I think that's a 20 mil shaft in them, so we can get out my it's a 25 mil shaft. So yeah, they're going to be able to, and that 25 mil shaft is going to be able to take a lot of ongoing force that's going to be put on these. So the main force, the only force that is going to be exerted on these is going to be coming down this way. So I had some smaller bearings as well, which were like a 10 mil shaft, and I was just looking at them one day and I just said, nah, no way, they're not. There's no way that's going to be strong enough over a really long term I want this to be a really reliable machine that I can use for hours and hours and hours and get a lot of life out of. So I thought, yep, we'll just make them up. So this sits here. This here is solid bar steel, and it fits. I need to just round the corners off, and it fits perfectly inside. It will fit perfectly inside this box steel. So this is 7 mil, and I think it's maybe 50 mil or 40 mil box steel, sorry. So this is incredibly robust, and then this will slide in and slide all the way down like that, and except be inside it, obviously. So this will go all the way to there and pretty much end up being flush. I mentioned in the last video that I wanted this arm and mainly these rollers, I wanted the rollers to be able to be adjustable, to come up and down. So that was a really important feature for me because I wanted that flexibility, and there's no way, there is a way, but it would have been incredibly difficult to calculate all of these unknowns and get it absolutely dead perfect to be working in its most prime performance, really. So I knew that I wanted to make it adjustable. So this is going to be able to come up and down here, and then on the face here there's going to be a lock-off bolt and a lock-off bolt that I can screw down to grab onto this. I also had another idea that I can't remember right now that'll help with keeping it in place. But anyway, but just those nuts by itself wouldn't be enough. So on the drawings I showed you that there's these really large nut things. So there's this, and this will be housed within a bracket that'll come off the side here, and the brackets will hold this firm but still let it be able to rotate. So it'll be the perfect length of it, it'll still be able to rotate, and as you rotate it, this bolt will move up and down. So ultimately, this bolt will be able to slide at really small increments up and down. And then there's a secondary lock-off nut. There'll be one there, and there'll be one possibly on the end if there's enough space. So you slide it up and down to adjust this wheel. So there'll be the bracket which holds this will be coming down here and then down here and connect to these bolts. So there'll be another face plate there which this wheel will connect to, and then as the bolts move up and down, this too will move up and down. So the sideways forces flexing this way and this way will be taken up by this, which is incredibly robust. I've got no issue at all with the strength of that. And these two bolts, there'll be another one on this side as well. These two bolts will only need to withstand the forces pushing this way, which I believe that they will. The compressive strength of a bolt like this would definitely be a few ton. So I'm really confident with that, and I think it's a pretty good idea, if I do say so myself. So that's ultimately how that's going to work. There's going to be another one. There's two rollers. There needs to be another roller down the other end, which is just a mimic of this. So yeah, and then lucky last, we have the pipe. So this is the one that I mentioned that I got off eBay. If you can look in there, it's incredibly thick wall. It's 40 mil internal diameter, and then I think it's 15 mil on the outside. Yeah, it is. It's 15 mil on the outside. So if I try and push this together, I can't even squeeze it together with my hands. So the reason for that is you want this to be able to depress and then it spring back. There's also multiple weavings of nylon woven core inside here as well, and so that gives it even more strength as well. And this is a natural rubber as well, a complete rubber, which makes it more expensive as well. So I mentioned before, these are normally about 800 to 1,000 to replace. to buy just from the factory, and I got them for $200 each, and I have 2 of them. So that's kind of it. Yeah, this is really, really exciting. I hope you are finding it interesting, and I hope you're learning something from it. And this is literally, I'm literally filming this as I go, obviously, and I'll be releasing it as I go as well. So if you've got any thoughts or ideas, chuck them in the comments section. I'd be really appreciative. And yeah, there'll be a lot of changes and a lot of shifts, but yeah, we'll get there. We'll get there eventually. I've got the steel to make the faceplate for this, like the plate that this bolts onto, and the undercarriage for this whole unit as well. Only thing I haven't bought is the frame for the steel for the frame, I mean. So yeah, we're just going to see how we go, and yeah, thanks heaps for watching, guys. Can't wait for the next one.